Thank you. I'm really excited to talk today about investigating the HIV epidemic in Miami using a novel approach for Bayesian inference on partially observed networks. I know that's a lot, and we'll sort of break it down throughout this talk, but I also want to sort of say it's a wonderful team that I get to work with on this project, and their names they're up there. So first, for a little bit of background or a little bit of motivation on why we're doing this work. So epidemic models, and I know some of you work on them here, they're very useful to develop effective interventions and assess their impact. And in particular around network models or network-based epidemic models can help inform network-based prevention and treatment resource allocation, such as the work around HCV for Treat Your Friend strategy that is modeled by Margaret Hellard. And as everyone knows, epidemic models, they need to be parameterized, and network models need also that, and in a particular one around that is understanding about the contact pattern or the network. And one interesting area that can help inform that information is molecular epi. And so molecular epidemiology supports the investigation of disease dynamics through providing important information on mixing/transmission patterns by linking individuals with genetically similar viral sequences. And to date, there's been very limited models that sort of use this. And one of the reasons for that is that there's a big limitation around using molecular sequences, and that is missing data. So not everyone, not every person living with HIV will have a reported and collected and stored sequence, and those that do is not uniformly sampled, and so it's not always a representative data set. And just to level set or give a little bit of background, what is molecular epi for those who are not super familiar with that, I want to just walk through a very quick illustration on how we go about creating these kind of viral genetic linkage networks to help understand a little bit about transmission patterns. And in network analysis, it's very common to represent individuals or as circles or nodes. And so that's what we have illustrated here. And so we have, and then you can, based on the characteristics of individuals, here we kind of color code the nodes. So here we have two sets of populations or characteristics. So we have men who have sex with men who have not reported any injection drug use. And then we also, and they're represented by the purple. And then the gray nodes are represented as men who have sex with men who are also a person with injection drug use. And here, just an illustration, we can look at the sequences of two individuals as represented here. And if they are similar to some degree past the threshold, we would link those two individuals. And then you can repeat this for all the individuals in your population. And this is, once again, just to put a caveat on here, is not saying that one person infected another. It's not about direct transmissions. It's a proxy for the transmission network. So two individuals that are linked are probably close in that transmission chain. But once again, as I mentioned, we don't get to see all the sequences. We have quite a bit of a subsample of sequences that are available. And here, this illustration is showing that of the purple nodes, about 50% have sequences, and of the gray nodes, about a third. And so when we compare the actual versus the observed networks, they can look very, very different in structure. And that leads to them being very different in network properties, which is what we need to know to be able to parameterize our epidemic models. So in this illustration here, we're interested in two network properties. One is around mixing, and the other one is about the number of linkages. And so just to tackle the first one, just to level set and give everyone an idea what I mean by mixing patterns. So here on the true one, which is on the top there, we can sort of understand the number of linkages between purple nodes, and there's 2 of them going from purple to purple. There's 8 linkages going from purple to gray, and then there is 1 going from gray to gray. And that looks very different from what we would observe in the actual data. So here we have both of them from purple to purple being observed, only 1 from purple to gray, and no gray to gray. So you can sort of see how this sort of non-representative sampling leads to biases in our inference on this network property. And we can sort of look at a similar kind of process on understanding degree distribution. And what that is the number of linkages, or the distribution of number of linkages. So in the complete or the true network, we would have no people without a link. So that would be degree 0 is 0. Everyone typically acquires it from somewhere, so you shouldn't have isolates. And then we have 4 people with degree 1 or connected to one other person in the viral genetic network. But in our observed network, you would have a very different look of that. And in particular, what you'll see is probably a spike on the number of individuals in the viral genetic network that look like isolates. So here we have 5 individuals that are not connected to anyone in the viral genetic network. So the aim of this project is to develop and validate a method to reconstruct the viral genetic network in order to estimate characteristics about the true underlying viral genetic network from this partially observed data, and then apply it to looking at to the HIV epidemic in Miami. So how do we go about doing this? What is our method? And I'm going to give a very high-level overview, and then I'll give a little bit of an illustration. So we're using the Bayesian paradigm, and we're using a very flexible network model that underlies our inference, and that's the concurrence class model that we've, as a team, has been working on for quite some for a while, and we're able to do this by some advances in graph theory. And this model is quite flexible, so we don't have to put a lot of assumptions about how we think the underlying network will look like. And what's really nice is that we have come up with ways to make this a little bit more computational tractable. To give a very high understanding of what the procedure does. And so what you want to look at is, so you have this partially observed network. But you know which links you don't know about, or what connections that may or may not be there. So what you do is that you look at all the possible ways that you can complete that network. And so there's going to be hundreds of trillions of ways that one can complete the network. And so that's where the computational efficiency comes in. But conceptually, you look at all of those different combinations. And then by looking at all of that, you can sort of put a propensity or a probability on each potential mixing matrix or mixing pattern and say, what is the probability that this one is the true underlying one? And that's the process that we go through to understand what are the potential values for an underlying network. All right, so we came up with this approach. Obviously, we have to think about how to validate it. And what we do is we use a simulation study. So what does that mean? We generated a full network, and then we subsampled that network. We subsampled it to be about 30%, which is what we observe in Miami of the number of people who have sequences. And then we used our approach to reconstruct the network. And here what I'm presenting is around degree distribution. So that's the number of linkages that a proportion of people who have 0 connections in the viral genetic network, 1, 2, 3, et cetera. And that's what's presented on the x-axis from 0 to 15. The true one is all the way to the left. The partially observed one is in the middle. And then you can see that spike all the way up on the proportion of people who are isolates in the observed network. It goes quite high. And what we do is in terms of our reconstruction. Not getting it perfect, but we're getting it much better, and it gets much better as you get more data. But we're doing, I think, pretty good given the amount of data that one is collected in terms of getting the right degree distribution. All right, now we're applying this data, or this approach to Miami to understand the underlying viral genetic linkage network in Miami. Okay, so first, a little bit about the coverage of HIV sequence in Miami. So about 30% of individuals have a sequence collected, stored, and reported. And that varies by race as well as transmission risk. So here we can sort of see in terms of by race/ethnicity that we can see that blacks have the highest coverage of sequence at almost close to 40, where white individuals will have it around 22% coverage. And these also vary by transmission risk, where we have men who have sex with men with no reported injection drug use is at 30%, and it's a little bit higher for men who have sex with men and have reported injection drug use. All right. So just to give some high-level results that we sort of see. So what we're going to see is on the left is if you just look at the partially observed network, so the data at hand, no adjustment, what you'll see is a lot of a sort of mixing by race. I won't go through all the points on there, but what ends up happening is once we do the adjustment, we see a substantial difference in the amount of mixing by race. And in particular, there's a lot more mixing across the races than what the observed data would indicate. For example, in the observed network, viral genetic linkages from black MSM have about a 5% probability of connecting to a white MSM. But in the reconstructed network, it's about 18%. And similarly, when we look across risk, we see, once again, a very different mixing pattern across individuals who are MSM and individuals who are MSM as well as a person who injects drugs. And so once again, looking at the observed versus what we reconstruct, there would be about a 2% mixing within the MSM and person with injection drug use compared to when we redo the kind of adjust for all the missing data, it bumps up to 33%. All right, so conclusions. What we did, we developed a Bayesian approach to addressing missing data. Once we do that, we see a lot more mixing across both race and ethnicity, as well as by transmission risk. And where we're going from here is we want to expand it. We mostly focused on MSM, and we want to kind of expand it to the entire population of people with HIV in Miami, as well as kind of explore how the different interventions may now be impacted with this additional information using epidemic models. Thank you.
Maybe we have time for one question.
Hi, Ravi, super interesting and congratulations, really lovely work. I was interested in when you're sort of doing the model, the undiagnosed, so when you've got your unobserved, but I'm wondering in Miami, I'm assuming that the model that you're doing it is with people who are diagnosed. So just wondering what's your undiagnosed, do you have any sense of what your undiagnosed, unobserved that you can't say anything about there? And do you think, where do you think that sits and how might it impact, and are you trying to figure out a way of how to deal with that?
That is an amazing question, and one we're definitely quite wrestling with. Even estimating the proportion of undiagnosed is as you know, is quite tricky, and I think most people use what is like the CDC CD4 depletion model, which has some really strong assumptions for estimating the proportion that is undiagnosed. So you're right, like the methods right now, we are just trying to understand among those that have been diagnosed, but we are working on how to sort of expand this to capture that and understanding whether we can sort of see gaps in the viral sequence that might give us indication that there might have been individuals who are undiagnosed that would fit kind of a little bit more into that viral genetic linkage network.
Fantastic. Thanks.